All right, so this is the first real new lesson that kind of builds upon the various things we've learned about and reviewed recently from Math 10 involving polynomials, especially factoring, and connecting it to something that you probably didn't do in grade 10, which are dealing with rational expressions and rational equations. And when you see the word rational, you can see the word ratio buried right in there. And a ratio can be expressed as a fraction, so in practice we'll be working with fractions a lot. And so if you look at these three expressions here, these are all examples of rational expressions. They're all fractions. And we have these polynomials inside them. Now, quite often when you have a rational expression, you have restrictions or non-permissible values, which mean the same thing, which are basically a statement making it explicit, making it clear about what number or numbers you cannot put into the expression, what number or numbers cannot be used to substitute with one of the variables. So for example, if I look at this, if I just leave it as it is, then I'm saying that a can be any number we want, any real number. But that's not quite right. I can, a is a variable, and I can substitute a with just about any number I want, except one particular value. And in this case, the only number a cannot be is a cannot equal 3. That's my restriction. And why is that? Because if we just look here, if a equals 3, my denominator becomes 3 minus 3. My numerator is 3 plus 2. And so I get 5 divided by 0. Now, I don't care about the 5. That's OK. But division by 0 makes no sense. This literally means you take 5 and you're breaking it up into groups of no size at all. Not even really small, absolutely no size. You can't take a number that exists, like 5, and break it up into groups that have absolutely 0 size. And so this just doesn't make sense. And division by 0 never makes sense. And so as long as we're not substituting a with 3, I can substitute a with any number I want. But I need to make it really explicitly clear that a cannot equal 3. And we call this a restriction or non-permissible value. Everything else is OK. So sometimes you could say then comma, where a belongs to the real numbers. So it can be any other number, any other real number except for 3. That said, if you don't say that, this is still implied. So at its most simplest, that's all we need to say. So let's look at this rational expression. 5b over 3cd. Well, again, we have three different variables, b, c, and d. The b can be anything. You can have a 0. Again, 0 divided by a number, I don't know, 2. This equals 0. This means you have nothing, and you break it up into 2 equal groups. Well, each group has nothing in it. That makes sense. But the other way around doesn't make sense. Again, you can't take a number and break it up into 0 groups, or groups of no size at all. That doesn't make sense. And so in this case, the b can be any real number. There are no restrictions on b. But c and d both cannot equal 0. c cannot equal 0, and d cannot equal 0. Because again, notice if c equals 0, I have 3 times 0. And don't forget your 0 times tables. 0 times anything is 0, easiest ones. And so as soon as c equals 0, I don't really care what that number for d is. The whole denominator will equal 0. And same thing for d. As soon as d equals 0, I don't care what c is. The whole denominator will equal 0. But b can be anything. So there are no restrictions on b. Again, you can't divide by 0. It just doesn't make sense. But you can divide with 0. You can share nothing with people, right? But you can't take a number and break it up with 0 groups. That's it. Last one. And so here again, I need to pay attention to my denominator. And my denominator can't equal 0. Now with this question, to find the restrictions, it's probably a little bit easier if I first factor my denominator. And that's a difference of squares. And so if I look at my denominator, I can write this as f minus 3 and f plus 3. All right, so what I wrote down isn't any better in itself, but it does make it easier to see my restrictions. Because again, if I look back to the previous example, I could just tell right here, as soon as c or d equaled 0, everything else, the whole denominator must equal 0 because it's 3 times c times d. Those are all factors. Same sort of idea here. F minus 3 and f plus 3 are factors. As soon as one of those becomes 0, the whole denominator becomes 0. Because we're multiplying f minus 3 times f plus 3. And so I can just tell right here that from this factor that f cannot equal 3. Because if f equals 3, that particular factor will become 0, and 0 times anything else is 0. And I can also tell from this particular factor that f cannot equal -3. Because again, same idea. Once that one factor becomes 0, since the rest is all multiplication, 0 times anything else is 0. So put that all together, we can say f cannot equal plus or minus 3. There's my restriction. And so the phrase restrictions are non-permissible values. They're interchangeable. I'll usually say restrictions, but you should just know they both mean the same thing. All right. So a rational expression, again, is essentially a fraction that involves polynomials. And going back to our work with fractions, this goes back to elementary school. You can express any fraction, any rational expression, in many different ways. For example, 1/2 is the same as 2/4. And I can prove that, quite quickly by just multiplying the top and bottom by 2. And as long as you multiply or divide the numerator and the denominator of any rational expression by the same number, you come up with an equivalent rational expression. So for example, if I multiply, let's say, the top and bottom by 3, I come up with an equivalent but different rational expression. In this case, I get 6/12. And I could spend the rest of my life doing this, so I'll just ... But all of those, 1/2, 2/4, and 6/12 are all equivalent. Same thing for 3/9. Again, I can multiply, or maybe this time I'll divide both by 3. Again, if you multiply or divide the numerator and the denominator by the same number, you get an equivalent fraction. In this case, you get 1/3. And I could then multiply or keep going. That said, you get the idea. I'm just going to highlight 1/2 and 1/3 because these particular rational expressions or fractions are in simplest form, or lowest terms. And again, that should be a phrase. That's not anything new. And what I have up here is elementary school math, but very, very important. And if you can express any, if you use the idea of expressing fractions in lowest terms, then we can express rational expressions in lowest terms. So let's look at this one, 2a over 4b. Well, I can divide the top and bottom by 2. If I do that, I get 1a, or just a in the numerator, and 2b in the denominator. And so that means this must be in simplest form. It's equivalent to what I started with, but it is simpler. And quite often, instead of just showing these division symbols, we just do it a little faster, and we realize 2/4 reduces to 1/2. I actually kind of prefer that because it's faster, but in the end, what we're really doing is we're dividing the top and the bottom by the same number. No different than what we did up here. And so a over 2b, we say, is in simplest form, or in lowest terms. Now that said, 3 over c over 2, this already is in lowest terms. So I can't make it any simpler than this. But I just want to show one example of how I can come up with an equivalent expression. I could multiply the top and bottom by any number I want. Let's multiply by 2. I'll be boring. And then I get 6 over, if I double the bottom, I get 2c minus 2. Or maybe I'll do it in 2 steps. 6 over 2 times c minus 2, which is the same as 6 over 2c minus 2. Either way, they're all equivalent. I can multiply the top and bottom by anything I want, as long as I'm not multiplying the top and bottom by 0, because then I get 0 divided by 0, and again, division by 0 doesn't make sense. But again, everything you see highlighted in yellow on this page, these are all in lowest terms, or in simplest form. All right, so now I really want to more focus on just simplifying fractions that have polynomials in them, or simplifying rational expressions, and stating restrictions if necessary. All right, so let's look at this first one, a to the power of 6b over a squared b5, b to the power of 5. All right, I could start showing that I can, for example, I could divide the top and bottom by a to the power of 2. However, what's a little faster is just to cross that out completely and cross out the 6 and make it a 4. Because when you divide by a squared, a to the power of 6 goes down to a to the power of 4. And again, I could also show that I'm dividing the top and bottom by b, because I can do that to both the top and the bottom. That b will cancel out entirely. Or what I'd rather do is just know what I'm doing, and just cross that out and change that to a 4. And again, my work though, I essentially divided the top and bottom by a squared, and I divided the numerator and the denominator by b. It looks a little bit messy, so what do I have here? I have just a to the power of 4 left in the numerator, and b to the power of 4 left in the denominator. That's in simplest form. That's it. If I just move on I am saying that a and b can be any number we want, but they cannot be. I have to state my restrictions, and I can see clearly from my final answer that b cannot equal 0, because I can just see right here. I don't care about the power of 4, 0 to the power of 4, 0 to the power of anything equals 0. However, what you may, it's easy to miss, is that a can also not equal 0. And again, because if I look back at my original expression, there was an a in my denominator. And yes, I canceled it out, but when I'm canceling it out, I'm basically just realizing that, you know, I can, how can I say it? I'm basically realizing that a whole bunch of parts of this are kind of canceling each other out. So I'm just kind of getting rid of them. I'm ignoring them to get to the most important part. But you also can't deny there was an a squared in the original expression. If you look at that original expression, I guarantee if you replace a with 0, you will be dividing by 0. And so there's two restrictions we have to state here. A cannot equal 0 and b cannot equal 0. And it's very easy to miss these sort of restrictions here, because if you just look at your final answer, you'll never see it. So the key is, don't just look at your final answer. Let's look at this one. Let's put this in simplest form. What can I do here? Well, it's hard to tell what's going on here. However, again, factoring tends to help. And so if I take my my denominator, I can factor that. And I can factor that by taking out a greatest common factor of a. And again, anytime you think of factoring, and we'll be factoring lots, always think of looking for a GCF at some point, if not right away. If I do that, I get a squared minus 2 in my denominator. And now I can see more clearly what happens here. I can divide the top and bottom of this by a. There's an a as a factor of a I can divide the top and bottom by. Or again, a little bit faster, is just kind of cross out that entire a right there with one of those. So there's just one a left in the numerator. And again, I'm canceling out factors, because I'm multiplying by a, I was multiplying by a in the numerator, and I did have an a down here in the denominator, so I might as well just cancel these two out. And so this simplifies down to 7a over a squared minus 2. So with that said, the restrictions here, a little bit trickier. First of all, if I look at just the a squared minus 2, all of that together can't equal 0. So I will say, I'll make a little note right here. A squared minus 2, that whole thing altogether can't equal 0. Which means if I add 2 to both sides, that means I know a squared can't equal 2. But what about a? Well, that means a can't equal the square root of 2, plus or minus. Now, I'm going to be honest here. At this early stage in the course, I'm not too concerned about if we're a bit confused about this restriction. This is what we call a quadratic equation right here, a squared minus 2, and this becomes a foundational aspect of this course, but we haven't got there yet. So in terms of restrictions right now, I'm not too concerned if that a cannot equal, I should say, plus or minus root 2. If you're not sure about that, that's okay right now, okay? Because it's honestly, it's a little bit beyond what we've done so far. Later on in the course, we can't just ignore it. However, there's also another restriction that I'm hoping is a little easier to see right there. I know I canceled it out, but there was an a right there. And if that a was a 0, it'd be 0 times anything else is 0. And so I have another restriction that a cannot equal 0. So really in the end, my restrictions are a cannot equal 0 and a cannot equal plus or minus root 2. But again, the plus or minus root 2 part, I'm okay if you're not feeling great about that. Like, we'll come back to that sort of stuff a lot more later on in the course. All right, last pair. Okay, so of these two, again, I want to simplify and state any restrictions. I'll do these one at a time. So again, a lot of stuff going on here. How to simplify, it's not so easy to tell until I think of factoring this. And so my numerator, take out a common factor of 3. 3 times x minus 2. And my denominator, this will take me a couple of steps because there's a coefficient of 2 in the front. And so I'm not going to be able to factor this just by looking at it. And so again, we reviewed this recently. How do we factor something like this? I'm always going to show the same shortcut. I multiply the 2 and the negative 10 together to get negative 20 I have to think what multiplies a negative 20 but adds to positive 1. So what are two numbers that multiply to negative 20 but adds to positive 1? Only two numbers are positive 5 and negative 4. Then I look at the 2 right here, and I divide each of these by 2, and now I inspect my factors. Or inspect these to determine my factors, I should say. So if I look at this right here, x plus 5 over 2. 5 over 2 doesn't reduce, but I swing up to 2, and I see one of my factors, 2x plus 5. Look at this one right here. 4 over 2 reduces to 2 over 1, or just 2 whole. So my other factor is x minus 2. OK, so now that I've done my factoring, now I can see that there's a factor of x minus 2 that I can divide from the top and the bottom, or just cancel each other out. Or x minus 2 divided by itself is 1. However you want to look at it. I don't need to worry about that anymore. And so this simplifies down to just 3 over 2x plus 5. That said, what are my restrictions? Well, one of them went back to this factor of x minus 2. If x equals 2, that factor there would become 0, and 0 times anything else in the denominator becomes 0. So one of my restrictions is x cannot equal 2. But another one comes from this factor right here of 2x plus 5. 2x plus 5 cannot equal 0. So if I subtract 5 from both sides, that means 2x cannot equal negative 5. If I divide both sides by 2, that means x cannot equal negative 5 over 2, which is the same as negative 2.5. And so that's another restriction. X cannot equal 2, and also x cannot equal negative 5 halves, or negative 2.5. I'm going to put negative 5 halves because we're dealing with fractions anyway, so why avoid them? And there's my answer. The simplified expression and the restrictions. So last one. 1 minus y over y squared minus 1. How can I simplify this? It's hard to tell again until I factor it. And so the numerator is already pretty simple. The denominator is pretty simple, but it does factor. It's a difference of squares. So it's y minus 1 times y plus 1. Now, nothing cancels out, although I will say that 1 minus y and y minus 1 are very similar. But they're not the same thing. You know, 2 minus 3 is not the same as 3 minus 2, but they're very similar. 2 minus 3 is negative 1. 3 minus 2 is positive 1. So they are similar, but they're not the same. But there is more I can do here. Because again, 1 minus y and y minus 1 are so similar. So for example, for 1 minus y, what I can do is I can take out a factor of negative 1 from it. And a good question is, why on earth would you want to do that? Well, you can take a factor of 1 or negative 1 out of anything you want. Taking a factor of negative 1 out of something just means you're dividing it by negative 1, which means you're just changing the sign. So instead of 1 minus y, it's now negative 1 plus y. Well, negative 1 plus y, since I have an addition statement, I can change the order of this around. And I can write this as y plus negative 1, or just y minus 1. And so notice what I have now is I do have a common factor. And I can cancel this y minus 1 now. Essentially, or going back to here, anytime you have two factors that are almost the same, just you have the opposite order of subtraction, you can cancel them out. They'll equal negative 1, because notice there's this negative 1 left right here. And so cleaning this all up, what do I have left? I have negative 1 in my numerator over y plus 1. And that's my simplified expression. With that said, my restrictions are y cannot equal plus or minus 1. And I can see that from looking at my factors right there. If y equals positive 1 or if y equals negative 1, I'm dividing by 0 at some point. But in general, anytime you have factors like a plus b over a plus b, that'll always equal 1. Anytime you have factors like a minus b over b minus a, that'll always equal negative 1. If you're subtracting two different factors, but in a different order, they will always just equal negative 1. And I kind of proved why algebraically up here. Now for the final problem, that's something I'd like to get to and talk about in person. So the final problem here, if possible, this is the sort of thing I'd rather just deal with in person instead of over a video. So I'm going to stop here.